Viitorul e al tău, noi punem temelia. UTCP, construim pentru România. UTCP, Universitatea de Construcții București.
Good afternoon, everybody. It's second time, because morning, afternoon. So I'll make a presentation on the behalf of our group of the university dealing with seismic hazard and seismic risk. I mean Alexandru Alda, Cristian Arion, and Florin Pavel. And the presentation will go through all the phases until to the calibration of the seismic action in P100 draft design code. A very brief introduction, then a few words about earthquakes, major earthquakes in Romania in the past century, how the seismic zoning of Romania evolved over time, site conditions, again in design codes in Romania, then the results of PSHA, then the final destination, P100 part 1 of 2025 seismic action. Now, there is no doubt that Romania is an earthquake country. This exercise from the past century, the exercise Kyriazis showed in the morning of 2020, everything pointed to Romania as a very seismic country, and Vrancea, a very, very high seismic area. And regarding to Vrancea, there were some remarks of Professor Pitilakis in the morning, some discussions with Professor Gazetas as well. Vrancea is a sort of weird uncle in the seismicity of Europe. It is a non-subduction zone. There is no clear, for the moment, mechanism for Vrancea. There are some competing approaches for Vrancea, but anyway, we have to evaluate the seismic hazard for the design. Why do we need this kind of seismic hazard? It's obvious because of the losses, in terms of human losses and in terms of economic losses. We have a lot of losses around the world, of course. If the country is unprepared, then you'll have a lot of losses. If the country is very well developed, you'll have a lot of losses. And you have the example of Japan of almost $300 billion in 2011. Some of the losses are insured, some of the losses are not insured. When the losses are not insured, the cost is on us. We might say that the cost is with the government, but the government finally is discounting the cost on the citizens, because the money shall come from somewhere. In 20th century, we have two major earthquakes of 1940 and 1977. This is very well known for the people working in earthquake engineering, not only in Romania. 1977 was a milestone in the developing of earthquake engineering. It is not our impression, it is the impression of the international teams from United States and Japan that visited Romania after 1977 earthquake. It was the record of 1977 at Încerc site here in Bucharest. At a first glance, seemed that it is something wrong with the record. We don't have this kind of very long control periods. And it was reprocessed in Japan and finally said, okay, this is the ground motion we recorded in Bucharest in 1977. And since then, all the approach in earthquake engineering changed in Romania. One particular aspect of the earthquakes in Vrancea is the depth of the earthquake, and because of this depth, the effects are spread on a very, very large area. You might notice that macroseismic intensities of 7 in distances in excess of 200 kilometers from the epicentral area. 1940 brought out the first accident for a reinforced concrete structure in Romania, a high-rise reinforced concrete structure, the Carlton building. Very high destruction in epicentral area. Panciu on the left-hand side was completely destroyed. more than 90% of the buildings were destroyed. In Focșani, a lot of damage. In Adjud, again, a lot of damage. And then 1977 came. With 1977, we have, of course, more points of observation, so we can describe the macroseismic intensities much better. Unfortunately, there is only one seismic record in free field conditions that was recorded here in Bucharest, in the eastern part of Bucharest, and as I mentioned, changed everything about the seismic design in Romania, that unique seismic record. A lot of casualties, more than 1,500 people died, out of which more than 1,400 people died in Bucharest. A lot of homes that were destroyed or severely damaged, and the total losses around 6 or 7% of the gross domestic product of Romania at that time. Both old buildings with no reinforced concrete design, as Kyriazis mentioned in the morning, this is the main issue with seismic risk reduction everywhere, but also some new buildings with some seismic design, fortunately only 3 buildings, out of which one was soft and weak ground floor buildings. At that time there was little knowledge about this. And the other one was flat slabs, and the third one, something very strange, out of 6 blocks, only one collapsed, having the same seismic design, and the issue was very, very debated at that time, why that happened. As I mentioned, the record was somehow with a lot of uncertainties. Is it real? Is it not real, the record? Because with the red line you have the design code spectrum, and with the red line what was actually recorded in 1977, both in terms of absolute acceleration and relative acceleration. What is the evolution of the seismic design code? I will say nothing about before 1977, because before 1977 we didn't have that wealth of knowledge generated by the earthquake of March 4, 1977. So since 1977, the seismic zonation was evolving all the time. You can notice a very high level of acceleration for that time. So this is 1978. In 1978, to have something like 0.32 G, it was quite a lot for that period. And all the territory of Romania was considered to be seismic. Then in 1992, a new version of the seismic zonation came out, and it was for the first time when the mean return period was explicitly recognized in 1992. It is 50 years mean return period. Then the revision of 2006, when the return period was elevated again to 100 years. And finally, 2013, which is the current seismic design code, with a return period of 20-25 years, namely 20% extents probability in 50 years. So still we have one more step to go to align with 10% extents probability in 50 years, and I'll share some results. Regarding the site conditions, with the site conditions, I have to mention that Romania benefited from 2 brilliant engineers, Țițaru and Cismigiu. And all the time I will say this. So these 2 brilliant engineers in 1960, in the Earthquake Engineering World Conference on Earthquake Engineering, they said for Romanian plain with deep deposits, quaternary deposits, the control period of the spectrum shall be 1.5 seconds. Never before, never existed, 1.5 seconds. Unfortunately, their proposal was not considered, and we moved to a control period much, much less than 1.5 seconds, and it was alternatively 0.4 seconds and 0.3 seconds. No seismic zonation in terms of soil conditions, because there were no records at that time. And after the earthquake of 1977, because of the unique record of in Cerc, here in Bucharest, They said, okay, control period 1.5 seconds. So as Tisaru Migiu mentioned, 17 years before. But the whole Romania was with 1.5 seconds because there was no other information. And then in 1992, because of the records of 1986 earthquake and 1990 earthquake, the territory of Romania was divided in three zones with control periods of 0.7 seconds, 1 second, and 1.5 seconds, as you can notice here. So 0.7, 1, and 1.5 seconds. With the revision of 2006, 1.5 seconds was elevated a little bit to 1.6 seconds. And we have 3 design spectra for Romania. And in 2013, almost no modification in the control period of the response spectrum. This is a brief history of the design spectrum in Bucharest. So a lot of modifications during the time that the normalized response spectrum for Bucharest in the period 1963 to 2013, the year of the last version of the seismic design code.
This is soil?
No, for actual soil, yeah. Then we had the opportunity, starting with 2012, to have a project together with our colleagues from National Institute for Earth Physics and Building Research Institute here in Bucharest to revise the seismicity of Romania and to revise the probabilistic seismic hazard analysis of Romania. And the project was completed in 2016, and it was a little bit revised in another project in 2016, but there were no major differences from Big Sis project to RORIS project. And the seismicity was revised. The ground motion prediction equations were tested or developed new ones, and we accounted for both random and epistemic variability in our PSHA. We considered all the seismic sources that were proposed by the National Institute for Earth Physics that might affect the territory of Romania. 13 shallow sources plus Vrancea, intermediate depths, seismic source. You might notice that Vrancea intermediate depths is overlapping with Vrancea intermediate depths, seismic source. We considered the many earthquakes for the analysis of the seismicity. These are the earthquakes that were considered for Vrancea, intermediate depths, and also shallow earthquakes, both in Romania, Bulgaria, and Republic of Moldova and Serbia for the shallow sources. And we come up with this final result for the seismicity. As I mentioned, 13 seismic sources plus Vrancea intermediate. You have here the completeness here of the catalog, the number of earthquakes considered in the seismicity analysis, the completeness magnitude, and the maximum magnitude we considered in the analysis. Both for completeness magnitude and maximum magnitude, we apply different algorithms in order to find out the best solution for these two parameters that you know that is very much influencing finally the Gutenberg-Richter relations. Here you have some examples for two seismic sources. On the left-hand side, Făgăraș Câmpul Lung. This is somehow in the central part of Romania, a shallow source, and Vrancea, intermediate depths. And we move forward to ground motion prediction equations. And for the ground motion prediction equations, we used records generated by Vrancea, intermediate source. And you might notice here that we have the epicenters of Vrancea earthquakes and the stations with 1 records, 2 to 4 recordings, or more than 5 recordings. And we constructed an accelerometric database with 704 accelerograms, out of which 344 were generated by Vrancea. The rest, up to 704 accelegrams, were collected from different other seismic sources that are consistent in terms of seismicity with Vrancea from Japan, New Zealand, Mexico, Chile, India, Martinique, and Peru. This is the structure of the accelerometric database. On the left-hand side, you might see the combination of magnitude and focal depths. In the center part, you may see the magnitude and the peak ground acceleration of the records we are using. And on the right-hand side, epicenter distance and magnitude. And we separated the seismic records in two groups. One group, fore-arc, so what is happening in the front of the Carpathian Mountains, and the back arc, what is happening in the back of the Carpathian Mountains, because there is a lot of evidence, not only from Romania, that you have different attenuations in the fore-arc and in the back arc, and in the back arc, the ground motions are attenuating much faster than in the fore-arc. And we come up with the ground motion prediction equations for the shallow earthquakes. These are the seismic stations and the earthquakes we are using in the testing, because for shallow earthquakes we didn't develop any kind of new ground motion prediction equation. And finally, we choose three ground motion prediction equations for Vrancea fore-arc, Vrancea back arc, and crustal sources. And with the testing of the ground motion prediction equations, we propose the weights for different ground motion prediction equations. For example, for Causi and Facioli, for crustal sources, we have 0.4 the weight. For Ambrasei et al, 0.4, and for Atkinson and Akarenboomer, it's 0.2. And in this way, we constructed the logic tree for the analysis. These are two examples. On the left-hand side, for intermediate depths earthquakes in Vrancea, three ground motion prediction equations. So two of them, the one developed for Canada for BC Hydro, and the domestic one, and with the blue line, Young et al, because we want to have a lower bound as well in this prediction. And on the right-hand side, the other three, Causi and Facioli, Akarenboomer, and Ambrasei et al. How the domestic ground motion prediction equation performs, you might see here. It's an earthquake of October 27, 2004 from Vrancea with a moment magnitude of 6. It was a very well instrumented earthquake with a wealth of data, and we have with green shadow, we have the 68 confidence interval for the ground motion prediction equation, and with the gray shadow, we have the 68% confidence interval for back arc ground motion prediction equation. And the ground motion prediction equation, I have to mention, it was developed for many spectral values, starting with a spectral value of 0 seconds and going up to spectral values of 4 seconds. Now, the elephant in the room, as Kyriazis mentioned, site conditions. We have very, very few data. We have a lot of data for Bucharest, but outside Bucharest there are very few data. So we use some national data and some proxy based on the same algorithm mentioned by Professor Kyriazis in the morning, based on the topographic slope. And because we needed this soil conditions in order to have a broad overview of how to use the ground motion prediction equations that depends on the soil conditions. And we had to fit the data. And this is the logic tree used for probabilistic seismic hazard analysis of Romania, different for crustal and Vrancea, for Vrancea different depths considered in the analysis, then fore-arc and back arc for Vrancea, and the ground motion prediction equations that we mentioned. So in this way, taking into account the epistemic uncertainties in the analysis. And we come up with maps of this kind. This is a map with the peak ground acceleration value with 10% resistance probability in 50 years. So this is not for rock conditions. This is for soil conditions. So this is directly on the soil. These PGA values with 10% resistance probability in 50 years. And maps for different spectral values. Here you have a map for a spectral value of 0.2 seconds, again with 10% resistance probability in 50 years. Some examples of hazard curves in terms of peak ground acceleration. We might develop any kind of hazard curves as a result of this analysis. You have on the left-hand side, you have Bucharest, and the current value of 0.3 seconds, 0.3 G, the design value for peak ground acceleration, and the revised value for 475 years, or 10% resistance probability in 50 years. And on the right-hand side, I represented for the 10 most populous cities in Romania the seismic hazard curve in order to enable the discussion about the different slopes of the seismic hazard curves in Romania. And I will come back to this issue a little bit later. Also, for the sake of the later discussion, what are the uncertainties in evaluating the PSA result? What is controlled by Vrancea? Because we know Vrancea better, even if it is somehow not very clear, but we have a lot of earthquakes, we have a lot of records, so we can control Vrancea better. So what is influenced by Vrancea has low uncertainties than the other sites that are not controlled only by Vrancea, but are controlled by some other seismic sources. You might notice that the uncertainties are much larger, for example, in Timișoara than in Bacău. Bacău is fully controlled by Vrancea. Timișoara, at least at the values of peak ground acceleration, is not controlled by Vrancea, it's controlled by local sources. What about the European seismic hazard model of 2020? We've been involved in different ways in the development of the European seismic hazard model, as Chiriazis mentioned. Laurențiu Danciu, who coordinated the European seismic hazard model, is a very good friend of Romania, I must say, because he graduated from Romania, and he has a very close cooperation with my colleagues from Institute for Earth Physics, with us, and there was a lot of input for Romania for the European seismic hazard model, and a lot of testing for the European seismic hazard model. And then we had an exercise in the end, because we are part also of an external group with Chiriazis to test in different countries how it is working. Everything is fine. At the bedrock, everything is fine. You may notice here the differences between our national model at the bedrock and the European seismic hazard model. Almost no difference. No difference. So if we stay at the bedrock level, there is no difference. But if we move from the bedrock level and, for example, we take into account the control period, it is not working anymore. And it is not working the correlation rate with VS30 as well. Because if you have H800 at 1 kilometer, of course, you cannot control with VS30 any kind of information if the bedrock is so deep as it is in Romanian plain, and not only in Romanian plain. And this was an issue that everybody was aware beforehand. And we discussed with Professor Pitilakis, and we discussed with Professor Paolucci, and it was not only for Romania, because Italy is sometimes in the same situation, and even Greece might be in the same situation. And I said, okay, if S alpha and S beta is not working, then you can use S alpha and the control period TC. So in this way, we are still in Eurocode approach, but we will not be in the Eurocode approach with S alpha and S beta. We will be in the Eurocode approach with S alpha and the control period TC. Then I mentioned that we have a lot of seismic hazard curves. There were 10 cities, and the slope was very different. And here you have a map on the left-hand side with the values of the seismic hazard, with the slope of the seismic hazard curves for the whole territory of Romania, ranging from values of 1 point something up to 3 point something. And if the slope is very steep, or the slope is very mild, you have a lot of influence when you are deciding upon the ratios of the seismic hazard values for different mean return periods. So for example, I took only 2 examples. If you have a slope of 2 or you have a slope of 3. If you have a slope of 2, the ratio between the value with 1,000 years to the value with 100 years is 3.16. If the slope is 3, so if it is very steep, then that ratio is 2.90. So it might seem to be a very academic exercise. Why does it matter? But it matters a lot, these things. And now I'm moving to P100 of 2025. So if we count from 1963, there were 7 different versions of the seismic design code. So you might say that there is a modification on average so the mean return period of the modification is 10 years. Okay? The last modification was in 2013. What happened since 2013? So we had a new PSHA in Bixis project and Rory's project, and we have a new strategy for seismic risk reduction that was approved and endorsed by the government of Romania, and the strategy is very comprehensive. But at one point, the strategy mentions that the next revision of the seismic design code shall align with the provisions of the Eurocode in terms of seismic hazard. So move to 20% extended probability in 50 years to 10% extended probability in 50 years. So when the revision was launched in 2023, it was an explicit demand from the Ministry of Development to revise the seismic hazard in order to make it with 10% extended probability in 50 years. There were a lot of many other issues that were asked by the client, in our case, the Ministry of Development. But I refer just to chapter 3, for seismic action. And we are working towards the revision. Now we are very close to the final phase of the project. So we had the first phase, then there were some modifications requested by the technical committees, by the entities we consulted during this period. Then we have a public inquiry. We move from the public inquiry, everything is fine. And it is a procedure. If you have a national code, you have to notify the European Commission through a system, and the European Commission must provide a no objection in 3 months' time. That the national code does not have any kind of conflict with the European version. And this was one of the reasons why we revise the seismic design code. But besides this, there are a lot of reasons regarding, let's say, different escape routes we had identified, not in chapter 3, not in the seismic action, in some other parts where you might apply some provisions in different ways. And if you apply some provisions in different ways, of course, you'll get different consumptions and you'll get different costs. And the current version of P100 Part 1 is somehow cutting all these shortcuts in order to make clear and to have no alternative option, because a standard might have different alternative options. You might do like this, or you might do like this, or it's up to you. If it is a design code that is compulsory, there shall be no different approaches. And first of all, we classified the counties in two zones according to the slope of the seismic hazard curve, very broadly, 2 and 3. Okay, so the counties in red line, we assigned a seismic hazard slope of 3, and the counties with blue line, we assigned a seismic hazard slope of 2. Because of this, we defined different importance and exposure class for defining the seismic action, with much higher values for counties situated in the blue part of the country, and lower importance and exposure factors for counties in the red part of the county. Also, we try to keep the same exceedance probability for red counties and blue counties. It's like in the United States, okay? Red and blue, but okay, it's not about politics. So try to keep the same exceedance probability for all the counties, irrespective what is the slope of the seismic hazard curve. And for example, if we refer to the buildings in importance and exposure class 1, we have an exceedance probability of 5% in 50 years for ultimate limit state and 40% in 50 years for serviceability limit state. That's a very long discussion here. If you look to class 3, for ultimate limit state is like Eurocode, 10% in 50 years. But if you look to the serviceability limit state, it is much, much lower than in Eurocode. Why is that? Because serviceability limit state is designing the buildings in most part of Romania, especially in areas situated close to Vrancea, Romanian plain, Moldova plain, and so on. So if we would increase to the level of the Eurocode, the factor to be applied was something like 1.35 on average. So the designers who had a lot of problems right now to design the buildings for Bucharest for serviceability limit state, not for ultimate, for serviceability limit state, they'll have a lot of problems to increase with 35% this. And we try to balance this. Then the spectrum is the spectrum of Eurocode 8, except we don't have TA. So we ignored that period from 0 to TA, because TA is a very, very low value. It's 0.03 seconds. So actually we have no buildings in that area. And since P100 is for design of buildings, you cannot design equipments, because the equipment might be with 30 hertz or something like this frequency. But there is no building there unless you are designing a cube of reinforced concrete. So TA is not in our design code. And previously, you notice that we had the seismic zonation. So we have isolines and different values. Now we prefer to have values for each administrative unit in Romania. So each city, each county, where is an administrative unit, you'll find a table with 3,300, something like this, values. And for each and every administrative unit in Romania, you'll have the values on the plateau for ultimate limit state and serviceability limit state, the control period for ultimate limit state and the control period for serviceability limit state, and if it is in a high seismicity or low seismicity, or every seismicity for each and every administrative unit. explain a little bit later on. And the design spectrum, you have Bucharest on the left-hand side, and Cluj-Napoca. Cluj-Napoca is somehow northwestern part of Romania. It is not very influenced by Vrancea for peak ground acceleration, but it is influenced by Vrancea for lower frequencies, so for longer periods. So if you deaggregate the seismic hazard for a spectral period of 1 second, for example, you will notice that Transylvania is not contributing too much, but Vrancea is contributing a lot. So it depends where are you looking at. This is why deterministic is not working in all the situations.
The amplification?
Yeah. For long periods. For long
The
periods.
spectrum shows that the reduction is not needed. It's always beneficial.
Yeah, in this
The
case.
answer is different.
Yeah, in this
They
case,
have done
yes.
it in purpose. Yeah. I like it. I like it very much. Yes. Contrary to the branch motion.
Why? It is not.
Because the branch motion, it does go, the 1.8 is fine,
Yeah,
but why should we start from a very small period?
because we found no reference for very. So I will explain this. So you mean about TB?
Why 0.5
TB.
seconds should be as high as a 1.8? I like the 1.8, it's fine.
Yeah.
But why 0.5 should be the same?
At the beginning of the plateau.
Oh, I see. Yeah. So there are
There wasn't
two reasons. The first reason is like this. That value is, let's say, 0.1 seconds. Okay? 0.1 seconds. So in between 0 and 0.1 seconds, you have buildings with no redundancy in most cases. And on the other hand, you cannot control what is happening there in smaller earthquakes. In smaller earthquakes, you might have amplifications in higher amplifications. So because of these two reasons, that you cannot control very well what is happening there, we rather prefer to have very short control period, TB. And also, we checked in ASCE, the version of South American Society for...
Because the Americans do the same thing?
Yeah.
You should do it as well?
No. You know, sometimes when
Don't answer.
no. So sometimes you find a reference and they say, okay, they did it like this. So you have a very strong argument. Okay, but no, the main the main argument is because actually there are buildings, so very few buildings with very little redundancy. So you rather prefer to provide more strength because you know that you have no ductility there. So provide more strength in that area. As I mentioned, the values are for each and every administrative unit of Romania. So these are the values for, so the plateau value for ultimate limit state with 10% extent probability in 50 years. The values for serviceability limit state with 70% extent probability in 50 years. Control period, TC. You notice that we have only 3 values, 1.8, 1.2, and 0.8 seconds at the ultimate limit state. And we calibrated this value using records. And we have a very empirical relation that the value for is 10% in 50 years, it's 16% higher than the value with 20%. So we use the previous donation with 20% and we increased a little bit. And for the serviceability limit state, again, using the database, the value with 70% in 50 years, it's 0.6 of the value of 10% in 15 years. And
you are not using the collapse, the collapse prevention.
No, just 2 limit states.
Why?
Because we notice that in Eurocode there are listed 4 limit states and only 1 is verified. So we listed 2, and both of
for industrial facilities, important industrial facilities, which may have a huge impact.
Yes, but it is stated in the opening remarks that it cannot be used for dams. It can be used with for industrial facilities.
Not nuclear facilities.
Yeah.
I'm not speaking for nuclear facilities, neither for dams. I'm speaking for industrial facilities. Let's say petrochemical.
So if it
the
is,
impact of the pollution and
they might use the consequence class, and they can increase, and they have to use the importance and exposure class, and they will increase the seismic action.
1.8 or whatever is in Eurobond?
No, 1.5, something like this. Yeah. So it's moving to the first important class, and this is a discussion that even it cannot be used for dams, even it cannot be used for bridges. It is used for everything because it is the only seismic summation. So
This one is used for bridges, this one?
it is used, but
They don't say.
it should not be used because this is just for buildings. It's P100 Part 1 provisions for buildings, provision for new buildings. But everybody is using this donation. Yeah, but P100 Part 1, because it depends on the Ministry of Development, is for buildings. It should be something related to the Ministry of Transportation in order to be valid for bridges. And it is not a common order between the Ministry of Transportation and Ministry of Development saying, oh, it is valid for everything. Yeah. Seismicity, low seismicity, moderate seismicity, and high seismicity. You may notice that the limits are a little bit different from the Eurocode. The reason for this, it is a national determined parameter, so you can use it, but the reason for this is the following. There are 4 programs run by the Ministry of Development for seismic retrofitting of residential buildings, schools, hospitals, so there are a lot of programs. And putting this limit in this way, what is a county or an administrative territorial unit that is eligible today would be eligible tomorrow after the adoption of the new seismic design code. All the results I presented here are, as I mentioned, in 2 research projects, and it is the merit of, as I mentioned, Alex, Cristi, Florin, from our group from the university, and the results contributed to the revision of Chapter 3 of the draft document, Seismic Design Code, Part 1, Design Provision for Buildings. And thank you so much.
Viitorul e al tău, noi punem temelia.